Good afternoon. Good afternoon. Hope all is well and everyone's doing all right. As always, going to wait for everybody to get connected and then we'll go ahead and get started. All right, we still got, let's see. Okay, still got a couple trying to connect. Let's give them a couple more seconds and then we'll get started. All right, yes, you said says assignments. Yep, those are all our assignments. We have homeworks and tests. Now I haven't posted all of your tests yet. Um, Hold on one second. I haven't posted all of your tests yet. You have one test posted. But your homeworks, all of your homeworks have been assigned. Yep. Mm-hmm. Mm-hmm. Yep. Nowhere else. Yeah. Was there something else you were looking for? I just want to make sure I got you. Okay. Okay. As a matter of fact, let me do this. Mm-hmm. So yep, right here, clicking assignments. And yep, this is all your stuff. I go to one test that has been posted and then everything else. Yep. Test reviews are not mandatory, just extra credit. All right, so yeah, you have to. Yeah, we can talk after that, after class about that. Yeah. Um, so, all right, so 3.2, what's unusual? Yeah, the definitions were a part of your assignment. So chapter 1, chapter 2 definitions. You do want to make sure you knock those out. Now, you can find those in the e-text. All of those answers in e-text. All right. So what's unusual? The empirical rule and z-scores. So you can copy it on its title. And I'm about to go to another set of notes for the empirical rule and our z-scores. All right. All right, so let's go to here. So let's get started with the empirical rule. So APP is approximately 68% of the data is within one standard deviation, SD, standard deviation of the mean. Approximately 95% of the data is within two standard deviations of the mean. And approximately 99.7% of the data is within three standard deviations of the mean. All right, there's a diagram that emphasizes these three statements. Show you that in a second, but give you a chance to write that down. All right. So scrolling up, of course, if I scroll it too far, somebody still copying, let me know. So here's a diagram that emphasizes those three statements. Notice we have our mean in the middle, and we have these percentages. Now, remember we talked about the normal distribution, and your bell-shaped curve is symmetric about the mean. So your mean is in the middle. These percentages to the right add up to 50%. These percentages to the left of it add up to 50%. Of course, you add it all together, you get 100%. So in blue, that's going out one standard deviation. We're talking about to the right and to the left, and that gives you 68% of your data. Notice 34 and 34 give you 68. Then going out two standard deviations gives us 95%. So if you were to add those four percentages together, you get 95% of your data. And then going out three standard deviations. Oh, didn't mean to go out that far. Add up those six, that gives you 99.7% of your data. And then notice it's 0.15 and 0.15 on the tails. That's 0.3. And that gives you 100% of your data. So all those percentages add up to 100%. And it's reflect about the mean, symmetric about the mean, which is in the middle. All of those percentages will always stay the same. That's your empirical rule. These percentages will always stay the same. All right, can I scroll up? So we're doing an example that emphasizes the empirical rule in the process. We just want to make sure everybody had a chance to copy. Everybody okay? Everybody good? Okay, so first example, the mean IQ score of students enrolled at University A is 100 and the standard deviation is 16.1. So notice they gave us the mean and gave us the standard deviation. Normally, once we get to this point, they'll give it to us. But if you had to find it, don't forget, we told you to use the app website calculator to be able to find those things. We're not asking you to calculate that by hand. All right. So DET determine the percentage of students who have IQ scores within 3 standard deviations of the mean according to the empirical rule. Determine the percentage of students who have scores between 67.8 and 132.2. Determine the percentage of students who have scores above 132.2. All right, give you a chance to write that down. All right, so let's get started. So now, like I mentioned before, they gave us standard deviation, they gave us the mean. And so that's what I wrote down here in the red. And I just used the, remember we talked about last class, we ended last class with notation. So I used the population symbol for our mean and for our standard deviation. Over here in blue, I was just re-emphasizing that if you were talking about sampling, it would have been X bar. And excuse me, couldn't hold it. I tried to hit the mute before I sneezed in your ear. Sorry about that. But then S for the sample standard deviation. All right. So if you go back to our mean or our empirical rule, and our mean is in the middle, and there is the right side of your mean and the left side of your mean. So I'm going to calculate the right side and calculate the left side, show you how to do that, and then we'll have all of our data values. So right side of the mean, which represent the one standard deviation, two standard deviation, three standard deviations above the mean. So you take your mean, add 16.1 to it, which is your standard deviation. That gives me 116.1. That's our first data value. Then add 16.1 again. That'd be 132.2. And then add it one more time. That's 148.3. So that would be one standard deviation, two standard deviations, and then three standard deviations above the mean. All right, questions on the right side, about the right side. All you're doing is taking your mean, adding the standard deviation 3 times to get those 3 values. And then to get the left side, you're going to subtract the standard deviation 3 times. And that represents, one standard deviation, two standard deviations, three standard deviations below the mean. So subtract the 16.1 once gives you 83.9. Subtract it again gives you 67.8. Subtract it one more time gives you 51.7. And those are the 3 values to the left of your mean. All right, any questions so far? All right, so just filling in those numbers. Let me erase this. So look at the bottom, we have our purple numbers to the left, green numbers to the right, mean in the middle with 100. And so that's how our values work out. And then, like I mentioned before, these percentages do not change. Those stay the same. Those are the empirical rule. These numbers down bottom change according to whatever our mean and standard deviations are. All right, so let's see something in chat. Yes, yep. To get the values on the left, you always subtract. To get the values on the right, you always add. Yep. And there's always your mean plus the standard deviation, plus the standard deviation, plus standard deviation. Left side is the mean, subtract the standard deviation, subtract it, subtract it. So, all right, any questions before we go to actually answering the questions A, B, and C? All right, so going back to our questions, we have number one, letter A, Determine the percentage of students who have IQ scores within 3 standard deviations of the mean according to the empirical rule. So now this one, we really didn't have to do any calculation to figure out the answer. It says according to the empirical rule. So if we go back to the empirical rule, we're going 3 standard deviations out. That's 99.7% of our data. So we really didn't have to use any of the calculations that we just found for A. The answer is just 99.7 because that's just based generically on the empirical rule. All right. Now B is a little more specific. Determine the percentage of students who have scores between 67.8 and 132.2. So we go to what we've already established here with our numbers. 67.8 is right here. 132.2 is right here. So we add up the percentages in between. And so adding up those, that gives us 95%, excuse me. All right. Questions on B. All right, and then C, determine the percentage of students who have scores above 132.2. 132.2 is right here. You're talking about above. So you take these two percentages and add them together. And that's how we got 2.5%. Any questions? All right, so we're good. All right, don't copy. Oh, somebody had a question. Let me see. Can you show very top of the page again? All right, is everybody okay before I go to the top of the page? Everybody good? All right. So no, this is where we started right here. Oh, someone said something. Okay. So are you, does that thanks mean you're good to go? Or okay, sounds good. All right, so let me go back to 155. No, so empirical rule, we got to go to z-scores now. Okay. I think I got this. Yep, so right here. So don't copy that title, 3.4, because that's not us. But I want to go to z-scores. All right, so z-scores, the distance a data value is from the mean in terms of standard deviation. So it's a standard way of measuring out data values and converting them to a way that you'll be able to actually compare data sets and groups of information. So the way we calculate is by taking our data values, subtracted from the mean, divided by the standard deviation. So that's the general way of looking at it. If you had a population, you would use population symbols, which is x minus mu divided by sigma. If we're dealing with sample, it would be x minus x bar divided by s. Either way, it's still the same process. It's your data value minus the mean divided by the standard deviation. So no matter what symbols you use, this is what the symbols represent. Just like I said, just trying to get you guys used to the symbols. All right. So two statements to know about z-scores. I believe MathLab asked about it. I know for sure they talk about the mean being 0, but anyway, your z-score is a unit list, and then it has a mean of 0 and standard deviation of 1. So when we get to actually applying z-scores and using them in application, when we go to the z-score chart, you'll see that in the middle will be our mean, and that mean, once you convert to a z-score, will be 0. So that's what we're talking about here, the mean of 0, standard deviation of 1. And whatnot. So, but you'll see more of that when we get further into the use of z-scores. All right, can scroll up. Let me know if I go up too far so I don't sample. Okay, so here's an example using z-scores. Determine whether the Angels or Rockies had a relatively better run producing season. The Angels scored 773 runs and play in the American League, where the mean was 677.4 and standard deviation was 51.7. The Rockies scored 755 and play in the National League, where the mean was 640, standard deviation was 55.9. So I'll give you a chance to write that down for those who are doing so. Then we will knock it out. All right, are we good? Let's get started. All right. So the first thing I did was just extract the information from the problem itself. So we have the Angels, and just in case, well, I know I didn't throw it out there, but just in case anybody didn't catch it, we're dealing with baseball here. And so when it comes to baseball, if you don't watch baseball too much, you have the American League, National League, and with the American League and National League, they have a little bit of different rules. Let's see, what's that last symbol? You talking about sigma, right down here? I don't know if that's what you're talking about. Greek letter sigma. Um, but yeah, so they have different rules in each league, a little different rules in each league. So it will be relative to figure out, how well you did in the American League versus the National League, and compare those leagues versus comparing the whole, sport itself. So we have the data. The data value for the Angels is 773, just the amount of runs they had. Then the mean in the American League, 677.4, standard deviation 51.7. The Rockies, the amount of runs they had was 755. And then in the National League was 640 as the average, and then 55.9 as the standard deviation. So we're going to convert both of those to z-scores. And we would do that. is by doing your data value minus the mean divided by the standard deviation. So for the angels, 773 minus 677.4 divided by 51.7, 1.85. And for the Rockies, 755 minus 640 divided by 55.9, which is 2.06. Noticing that statement at the bottom, we always round our z-scores to 2 decimal places. So that's something that's going to matter when we actually start doing applications. So we might as well get in the habit of doing that now. So that's why I got 1.85 and 2.06.
Sorry, I'm running a little late. My relief didn't show up to work, so I had to stay. I'm sorry.
Oh, you're just gonna fail the whole class then. I mean, that's just it. I'm just messing. Thanks for letting me know. Yeah, not a problem at all. Thanks for letting me know. All right. Any questions before we scroll up and then come to our conclusion? So we've taken the Angels run producing year, converted it to a z-score, we got 1.85. To the Rockies run producing year, converted to a z-score, we got 2.06. All right, can we scroll up? Everybody okay? All right. So what this says that the Angels scored 1.85 standard deviations above the mean, and the Rockies scored 2.06 standard deviations above the mean. So it is possible for your z-score to be positive or negative. If it's negative, that means below the mean, and if it's positive, it means above the mean. We talked about being above and below the mean, earlier this session. So if it's positive, that means that's that amount standard deviations above the mean. So we have 1.85 standard deviations above the mean, and then 2.06 standard deviations above the mean. And that means the Rockies had a better run producing year. All right, so everybody good before we go to the next piece? All right. Oh, somebody said something in the chat. Standard deviation. SD is standard deviation. All right, so this is the next piece right here. Oh, that came from what we talked about. It's just a way to measure the spread of your data. Just a way to measure the spread of data. We talked about that last class in the earlier part of it. Yep, that's just another way we use to measure. Same thing with the variance, even though variance wasn't mentioned today. Just another way to measure the spread of our data. So yeah. And so that's why it was discussed in terms of standard deviations, how far something is away from the mean, the average, how far are you away from the average, whether it be above or below. So you can use a standard deviation to do your comparison in that way. All right. So here's another example using z-scores. It says the mean daily temperature of San Francisco is 65 degrees Fahrenheit, and the standard deviation is 8%. I said 8%, 8 degrees. On one day, the high temperature is 49 degrees. What is this temperature in standard units? Standard units means z-scores. And assuming the empirical rule applies, does this seem unusual? All right. So once again, we have our mean daily temperature, which is our average. It's at 65 degrees. And we have our standard deviation, which is 8 degrees. And we have a high temperature of 49 degrees. And we want to know what is it in standard units? In other words, what's the z-score for 49 degrees? And is this unusual? So first of all, we pull off our information. Mean 65, standard deviation 8, data value is 49. Then we convert it to a z-score. Looking for my pen. Don't see my pen, I just had it. Here it goes. So convert to a z-score right here, data value minus the mean divided by standard deviation. 49 minus 65 divided by 8, and that gives us -2, and it's -2 even, so that'd be 0.0. Remember, we said we're gonna take our z-scores to 2 decimal places. So it's -2.00. And so just give you a chance to copy that just in case, and then we'll look at the explanation. All right. So according to the empirical rule, 95% of the data is between -2 and 2 standard units. So this would be considered an unusually cold day because 95% of the data is between -2 and 2. So that's going to be our marker. And so I did a little bit of a diagram right there. So if you're talking about -2 or less or +2 or greater, that's going to be considered unusual. And then, what's normal or usual would be everything in between -2 and 2. And so that's what I was saying right here. Your z-score being 2 or -2 or greater or less would be unusual. All right, any questions before we go to 3-3? All right, so 3-3 is summaries for skewed distributions. We've already did median. Remember I told you when we talked about mean, mode, and median. that median was actually going to show up in another section. So it actually shows up in 3.3. So we already talked about median. We're going to talk about IQR in a second. I'm probably going to hit the range first, but just giving you guys a chance to copy this title before we go to range. I think we may have already did right now. I might have skipped it just because I knew it was coming up. All right, so can we go to the range? Everybody good? All right. Nope, it's over here. All right, so here's the range. Range is just the distance spanned by the entire data set. To calculate your range, you would take your largest value, subtract the smallest value from it. And so here's a small example of that. We have a data set of 1, 2, 3, 4, 5. Do 5 minus 1, largest value minus smallest value, that'll be 4. All right, anybody still holding on to the range? All right, so let's go here. Look at our quartiles. So your quartiles divide the data set into fourths. All right, so notice a little diagram here. We have our minimum, maximum values at our bookends, and then Q1, Q2, and Q3 are in the middle. So to find our quartiles, we want to list our data values from least to greatest. Always remember that. Don't forget it. A lot of times people do tend to forget it. So don't forget that first step. You want to list your data values from least to greatest. Then to find Q2, you want to find Q2 first because that's the median of the whole data set. It splits your data set in half. Then you go to find Q1, which is the median of the first half of data. Then find Q3, which is the median of the second half of data. All right, can I scroll up? Now your IQR, your interquartile range, is the range of the middle 50% of the data set. So you'll find that by subtracting Q3 and Q1 from each other. All right, scrolling up some. And then the last thing dealing with IQR and quartiles. We can use them to check for outliers. So remember, outliers are extreme values, very extreme values in comparison to your data set. So they're very, very large or very, very small values, once again, in comparison to your data set. So instead of eyeballing it though, and just looking at it and say, hey, that looks like an outlier, we can create these boundaries or fences. I think other books call them limits or whatever the case may be. Yeah, upper limits, lower limits. So I forgot which one your book says, what boundaries I might be. Anyway, so if it's an upper fence, to find the upper fence, you take Q3 plus 1.5 times the IQR. 1.5 comes from the formula. Then you, to find your lower fence, that's Q1 minus 1.5 times the IQR. And so these are just boundaries or fences or limits when you can establish and say if a number is larger than this upper fence, then it's an outlier. If a number is smaller than this lower fence, it's an outlier. And that's what this green statement says. Two green statements say. So once the data value is greater than the upper fence, it is an outlier. If it is less than the lower fence, it is considered an outlier. All right. Any problems with anything that was written before we go to the next thing? I'm going to do an example with this stuff, but I just want to make sure everybody has written all they're going to write. All right, let me see if my example is good right here. Nope, nope, comparing measures. Yep. All right, comparing groups. Spot number summary. Okay, so let's. All right, so let's walk through this example right here. So first step is you want to list your data values from least to greatest. I've already done so in this case, but it's no guarantee that you're going to get a data set that's automatically listed from least to greatest. So always make sure that's the case. I've already done it for board purposes. Don't want to have you rewriting, the same data values multiple times for no reason. So let me erase some of these circles as well. Also, I had 18 data values. And so what I did here was I went ahead, as I was writing, I went ahead and broke it up into halves. So it's up to you if you want to do it that way, but I think it is beneficial when you start trying to figure out what's my middle values, where are my middle values and stuff like that. So that's why I set up my data values and I already break them up as I go about listing them. So if I have 18 data values, I already know I have 9 in the first half, 9 in the second half of my data set. Okay. And that's 180, 189, 370, 618, 735, 802, 1185, 1414, 1657, 1953, 2332, 2336, 3461, 4668, 6751, 99, 808, 10,034, 21,147. All right. So We want to find our quartiles. Remember, we have to find Q2 first. And I tried to color code, not color code what I was doing. So Q2 is the first one that we have to find. Now we have 18 data values. So that means we have an even number of data values. And if you have an even number, that means you don't have a middle number, a legit middle number. So you have to take your two middle numbers, add them together and divide by 2. And that's what we did here. 1657 plus 1953 divided by 2 is 1805. Once again, you have to do that when you have an even number of data values. You have to take your two middle numbers, add them together, and divide by 2. Now, when I look at the first half of data, second half of data, I have to find my medians of those two. So Q1 is going to be the median of the first half of data. I have 9 data values there. So that means I have a legit middle number. I have an odd number of data values. So I have a middle number. That middle number is 735 for my first half of data. And then for my second half of data, the middle number is 4668. Any questions? Any questions? All right. Step 5, find the IQR. That's just doing Q3 minus Q1. So that's 4668 minus 735 gives us 3933. All right, so everybody good. And now we can determine our fences or our boundaries for our outliers. So our upper fence, Q3 plus 1.5 times the IQR, that ends up giving us 10,567.5. Anybody holding on to step 5? All right. And then our lower fence, Q1 minus 1.5 times the IQR, ends up giving us negative 5,164.5. All right, any questions, questions? All right, are we good? Okay, so then the question is, do you have any outliers or are there any outliers? The answer is yes. So you take your fences. We have 10,567.5, negative 5,164.5. Go back and compare it to your data set. If anything's less than that lower value, then it's the outlier, but anything greater than it, then this upper value is the outlier. And so we have this number, 21,147 is greater than this fence right here. So that means it is an outlier. All right, questions.
What about lower outliers? Isn't that showing that just about everything is a lower outlier? If the lower fence is 5164.5?
It's negative.
Oh, it's
though.
negative.
Yeah.
My mistake. Okay, there we go.
Yep, not a problem. But you're most definitely right. If that wasn't a negative there, we should have a low. Well, let's go back to see. Yeah, we would have a whole bunch on that's less than that. Yep. But that negative is what saves us. All right. Questions before we go to the next thing. All right. So that's it for 3-3. We got 3-4. Because 3-5 is the same thing that we just did. Okay, so yeah, let's go ahead and do 3-4. 3-4 didn't have much calculation, just a couple of statements that I pulled out, these three statements. And then we already talked about being resistant to outliers. That's back at 3.2. I went ahead and went over that when we did. Let me show you just in case. Stuff, just to remind you. When we did our mean, mode, and median, we did resistant to outliers and stuff. So that's back in those notes. All right, so let's look at these couple of statements and then we'll 3.5 is the same thing that we just did. It's just that it adds one more thing, but it's not really a step, just notation. So I'll show you what that is and then we'll be finished. So comparing measures of center in a symmetric distribution. You know, we talked about that before as well. Normal distribution, bell-shaped curve. The mean and the median are approximately the same, AVP approximately. All right. In a right skewed distribution, the mean tends to be greater than the median. In a left skewed distribution, the mean tends to be less than the median. I'll scroll up. Is everybody done with the title? Okay, so there we go. All right. Anybody still copying? we check that. Okay. So last statement out of this section, we're comparing groups. If any one group is strongly skewed or has outliers, it is usually best to compare the medians and IQR for all groups. So remember, the medians are resistant to outliers. Your means, your averages will be changed according to the numbers that you have, very, very small or large numbers. All right, can we scroll up? Last thing for today, box plots and the 5-number summary. All right, so let's go ahead and knock this out. Nope, wrong section. All right, so y'all don't need your title. 5-number summary. So 5-number summary is your minimum value, Q1, Q2, Q3, and then your maximum value. All right. Box plots. Graphical tool used to compare groups of data. It consists of a box with lines that extend to the minimum and maximum values that are not outliers. It's called a modified box plot. These lines are called whiskers, and then outliers are represented by an asterisk. I'll show you a diagram of that in a second to give you a chance to write that down. All right, so here's a generic way of representing your box plot. Notice we have our vertical lines of our box is represented by Q1, Q2, and Q3. Then we have our lines, horizontal lines extending from the box to your minimum and maximum value. Those are your whiskers. And then if you have any outliers, those are represented by asterisks. Any questions? Any questions? All right. So let's walk through it. I'm going to give the 5-number summary and sketch the box plot. So notice they didn't mention anything about quartiles, but in order for you to get the 5-number summary, you need your quartiles. So because they asked for the 5-number summary and the box plots, that means we have to go pretty much do what we just finished doing those steps of finding your quartiles, IQR, and all the good stuff like that. So they asked for it without actually asking for it. So we're going to walk through that same process. They said get the 5-number summary and then sketch the box plot. Notice that statement that I just wrote, not just wrote, the statement that I haven't read. Data set is not always written from least to greatest. Make sure this is the case before you move forward. Remember, that's always going to be a necessity. Your first step has to be write your data values from least to greatest. All right, so right down that statement. Okay, so once again, I wrote my data set already from least to greatest, and I wrote it in such a way that I have half of my data set and then the other half of my data set. Once again, you don't have to write it this way. You do have to write it from least to greatest, but if you don't feel like splitting it up in half or whatever, that's fine. But it's up to you. I think this way does help. So notice I have half of my data set here, half of my data set here. And since I have 21 data values, I went ahead and counted out how many data values I had. I knew I was going to have a middle number because I have an odd number of data values. So I went ahead and put that in the middle. That's less than I'll have to look for later on because I'm going to need that middle number. So my first half of data has 10 data values in it. My second half of data has 10 data values in it. Then I have my middle number, which is my 21st value. So just like before, I color coded what I did. The first thing we want to do is find Q2. That's the data value that splits up our data into halves. So our middle data value is 30.95. Once again, I had 21 data values. I had an odd number of data values. So I did not have to do any calculation, just find the middle number. And that was 30.95. Now, because my first half of data has 10 in it and my second half of data has 10 in it, that's an even number. So I'm going to have to take the two middle numbers, add them together and divide by 2 because there isn't a legit middle number there. So Q1 is my median or my middle number, my first half of data. So I took 25.83 plus 26.28, add them together, divide by 2. That gives me 26.06. All right, do the same thing for Q3. Took the two middle values in my second half of data, 37.05, 37.43, add them together, divide by 2, gives you 37.24. All right. Find the IQR. Take Q3 minus Q1. That gave me 11.18. All right. So now we can establish our fences or limits or boundaries, whichever way you reference them. Q1 minus 1.5 times IQR is our left fence or lower fence. Q3 plus 1.5 times IQR is our upper fence. So far, our lower fence, that ended up giving us 9.29, upper fence 54.01. And that red statement is just reemphasizing what we talked about already. If a value is less than the lower fence or greater than the upper fence, it is considered an outlier. All right, any problems with step 6? All right, so step 7, determine if you have any outliers. So it's 54.63 is an outlier because it is greater than that upper fence. We had an upper fence of 54.01. All right, so everybody okay to go to the 5-number summary? We've done all our steps. Now we just need to list out what we have. All right. So the 5-number summary has nothing to do with whether something is an outlier or not. It's just what is the smallest value. That's number 1, Q1, Q2, Q3, 3, that's 2, 3, and 4. And then what is the largest value? That's 54.63. So once again, your 5-number summary has nothing to do with outliers or not. Just what is your smallest and largest value and what are your quartiles? And then your box plot, your modified box plot, your vertical lines for your box, Q1, Q2, and Q3. Then your whiskers, your horizontal lines extend out to the numbers that are not outliers. So that 1995 on the left for your minimum. And then the largest number that's not an outlier was at 49.17. So that's what it extends to. And then your outliers represented by an asterisk. All right, questions on anything? Questions on anything that's been written? So everybody's good, everybody's straight. Let's scroll up. Everybody okay? All right. So, as a matter of fact, let me check something real quick before I. Okay. Yep. I didn't put that there for you guys, so it's good. I don't have to talk about it. So, what we talked about up to this point, or what you guys are held responsible for up to this point, is chapters 1, 2, and 3. So let's say something in the chat. Yep. Office hours. Canvas announcements. I put the office hours up there. So, yep. All you do is click on the link for office hours, and I'll be there. If you know you're gonna run late to them, let me know. Yep, no problem. Shoot me an email. Like if you know you're gonna be like an hour late or something like that, let me know. Because if after an hour or so, if nobody's coming, then I might click off. I mean, just sitting there looking at a blank screen. But you know, if you know you're gonna be coming, feel free to shoot me that email. So I'll sit there and wait for you, whatever. But yeah. So what I do ask for office hours though, is to make sure that you bring your questions ready versus saying, "Oh, I just have a question on," and this is not just you. I don't know, I'm just talking in general for everybody. Make sure you bring your questions. So, and that's saying, I got a problem with quartiles. Well, don't tell me that because that's kind of real general. Like go into math lab and have problems ready for us to go ahead and attack. Because it's possible you come to office hours, could be more than one person there. And so what I would do is go to each person, take turns and just go to them. Now, if you can't make office hours, then you always can shoot me an email to try to make, create another time for us to meet. But I always ask that you bring your questions. So go into math lab and say 3.1, number 4. So we can just go ahead and do that problem versus just saying, generally, I got a problem with z-scores. Well, I don't know what your problem is, so, and you may not know what your problem is unless you actually have a problem for us to address. So yeah, always feel free to come to office hours, but I just ask that you have your problem so we can just go ahead and address your issues. And then if you've never went into math lab, you may not even know if you have an issue or not. You might be good, so yeah, so make sure you go into math lab, bring the problem so we can just go ahead and knock those problems out and make proper use of both of our time. So yeah, that's all I ask. Whatever problems you bring, I'm not going to ask you where you got them from. I'm not going to ask you is it the test problem. We'll just do it, knock them out. So yeah. So up to this point we have talked about or addressed 1.1, 2, and 3. Test 1 is already posted. Definitions, if you haven't gotten them to me, get them to me. Don't have to worry about test 2 yet because that has chapter 4 on it as well. You guys, that's 4.1 through 4.4 for chapter 1. So there's only 4 sections in chapter 4. So next class, I'm going to open up the floor for questions first. See if any questions have been generated over the weekend. Somebody say something?
Yeah, Professor, is that the email we send the definitions to, you, Tucker?
Yeah, that's fine. Or you can just do it through Canvas. Either way, it's fine.
You can upload it through Canvas too?
Well, no, you can send me messages. Some people communicate to me through Canvas. So I was just saying, if you decide to do it through Canvas, or if you email me here, it goes to the same address. So yeah.
Oh, okay, you mean the Canvas email?
Yeah.
Okay, I go ahead and get that sent to you now. Thank you.
Okay. Yeah, no problem. No problem. But yeah, so test 2 has 3 and 4 on it, so you don't have to worry about test 2 just yet. Don't forget, 8/5 is the due date for everything. If you want to gauge whether you're behind or not, you always look at where we are in the lecture. You want to be around that. You don't necessarily have to be ready for chapter 4, done with all of chapter 3 and ready to jump into chapter 4 by next lecture. I'm just saying you should be around that, in the vicinity of chapter 3, not, getting into chapter 3, doing chapter 3's work, because, we're done with chapter 3 now. But next class, I'm not trying to knock out chapter 4 next class. I'm just telling you next class, the floor will be open for you guys to ask whatever questions you want to ask. So I know somebody mentioned tutoring. That will be an opportunity to ask questions as well during class time. Once again, I just ask that you bring whatever questions you may have, to the table versus asking generally. So does anybody have any questions right now before I send you off into the weekend? I know I have one student that has a question, but that's a personal one, talking about class questions. Anybody? Everybody good? Everybody straight? Okay. Well, if you guys are good, I'm good. You know what you have to do up to this point. Like I said, try the stuff out, see if you get stuck, and bring those questions to class if you have them, and we will take care of those. Let's see. Yep, no problem. Thank you. Thank you. So you guys have a great weekend. Be safe, and I will see you next class.
Thanks, Professor. You too.
Thanks. You the same. Thanks.